Welcome back. Glad you got past the course description. So let's talk about the actual content now. This is object-oriented programming, learn programming in Java. All right, let's get started. Let's talk about what it's an object, and basically we'll talk about object-oriented programming. What topics are we going to cover in this course? We'll talk about what OOP is, just the bare minimum. You need to get you some baseline so the language makes sense. We'll have examples of each idea, and then does it all matter? Well, it does to some point, but we're not going to go too far. We'll talk about what a class is, inheritance, interfaces, and then kind of summarize those things. So we need some basics in Java, in OO, before we get to all the syntax. So let's get started. Okay, what is OOP, object-oriented programming? It has these characteristics. So not all languages have them. Some are base, some are pure. But in terms of what you need to know from Java, you need to know that object-oriented programming in Java has objects. These are instances of classes. Talk about that later. We have data abstraction or encapsulation, which is kind of information hiding. Funny word, but it's an important word, polymorphism. That's where the same message can be sent to different objects, but they result in different behavior depending on what object is receiving that message. Hold on from that thought. I'll give you some examples that'll make more sense. Kind of important. Inheritance was one of the most important things people thought object-oriented programming would give them in terms of value and reuse. Probably not as important these days now that we've been doing a lot of programming, but still nonetheless quite important. I think dynamic binding, probably the most important part of the language in terms of OOP, is the ability to send objects a message without knowing the specific type. What does all that mean? Let's get to some examples, but basically these principles are what makes an object-oriented programming, and this is why Java is what it is. It supports these things. Let's just cover enough of this so that you can get your job done. Okay, I promise you some examples. So objects are instances of classes. Classes are types. They're kind of like the structure or the blueprint. And objects are instances or examples of those structures or types. Now, in the real world, you're just going to hear objects and classes, but in this OOP class, well, let's give you some very simple classes and examples. You may or may not actually use them in the real world, but I'm trying to keep it simple. If I get too deep, it doesn't really quite make sense. So, what's a type? A canine is a type, right? You don't actually see a canine in the real world. That doesn't really make sense, but you know what canines are. But you do have a dog, and its name is Rover. So that's an instance of a canine. That's real. That's an instantiation of a class. You owning a dog named Rover means that you have one instance, a very specific, lovely dog, but it's a canine. You may go to New York University, but in general, you go to university. Now, would you go to a generic university? Doesn't make sense, but you know what a university is, but your particular university is New York University. Why do I have the tag LUV trucks for automobile example? It's because I can't just say a Ford F-150 is of an automobile. It needs to be specific. All right. So in this business example, I am modeling specific vehicles with a license tag. So a Ford is an instance of an automobile type. Now maybe the laptop you have is a Dell 1551. That's an instance of personal computer. So do we actually do these things in the real world? Do I have canine class? Have I ever coded up a personal computer class? Not likely, but I think these are good examples of classes or types or structures, and examples or instances of these classes and structures. So take a look, let it sink in, and when you're ready, let's go to the next page. Okay, let's talk about abstraction examples. These are not specific to OOP. You can do them in non-OOP languages. You could do this in your life. Data abstraction or encapsulation promotes information hiding and modularity. What does that mean? I mean, why do I want to hide my information? Don't I need to expose my information? And I don't like hiding things from people. You want to put the details of how you get something done away. You want to let people know, I do something for you. Don't worry about how I do it. Don't worry about the specifics, but I give you a contract. You give me some variables. I do something for you. You're happy and I'm happy. If I want to change how I do things later on, I can change it, but as long as you and I agreed that when I call print and you give me a document and assign a printer, I will print. Also, if I give you a log statement and you give me a message, now, do I have to open up an IO stream or log to a file, use some third party? Who knows? Who cares? But as far as you're concerned, you're a little function. I give you a message of type string and you log it for me. You give me a document and a printer, you call print, I will print it for you. How does it actually print? I don't know. Doesn't really matter. But this little contract hides away the details and implementation of that. Why is that important? Because later on, if I want to change that implementation, if I want to make it faster, I want to make it smoother, as long as you and I have always agreed on this contract, then it works. So when you pay the lawn man or lawn person $100 a month, now whether that person does it all by himself, gets a team of 20 people, don't care. I just need the job done. And as long as we agree on the contract, $100 a month, and you get the job done, does it really matter to me how it gets done? Absolutely not. That's data abstraction. It's a principle of OOP, but it applies to a lot of places and a lot of other instances, and not just OOP, but I think an important concept for you to understand. Okay, now we're getting to some really deep concepts, but these are important for the language because they happen everywhere. Funny word, polymorphism, many shapes. The same message can be sent to different objects, remember what those were, resulting in that behavior, but depending on the object that's receiving that message. What does that mean? Take a look at this classic example of polymorphism. If I give you a message and I tell you to speak, and you're a dog, well, you might bark. If you're a person, you might tweet. And if you're a bird, you're going to chirp. But what's common amongst all those things? That they all speak. How they speak is dependent on the type that they are. Don't confuse this with the previous one about implementation. That's not what this is about. I have the same contract. Whether I'm a dog or person or a bird, we all speak. Now, the classic example is fly, and then what do you do with the penguin? I don't want to get into that. It's kind of funny, not funny. But in OOP, if you define a contract, a method, a function that's called something kind of higher level. So I mean, you got to design this out. This doesn't just happen out of thin air. I know I'm looking at dogs and people and birds. They all have something in common. And if you give me a message and you tell me to speak, depending who I am, I will do what I need to do to get that speak to happen. A dog is going to bark, a person is going to talk, and a bird is going to chirp. They all are speakable. They will all speak, but they're going to do it differently depending who they are. But what's important here is that you're sending the same speak. You're calling the same speak method on all of these object types. So I don't need to know if you're a dog or a person or a chirp. I just know, listen, you promised me that you'll speak. You're doing that, and each one of you does it in their own way. And I'm just happy that I can just say speak. I don't have to say create a bark method. I don't have to create a talk method. I don't need to create a chirp method. That would be cumbersome. That's a lot of work. That's a lot of maintenance. What if we just all agree that we can all speak, and that depending what class we are, we'll do our thing the way we need to do it. So hold on to that thought. We're going to see more examples of this in the language, and it does come up. So this is not one of those theoretical things. You do need to know. You do need to. All right, let's talk about inheritance. This is something that I think conceptually makes a lot of sense. At the beginning of OOP, the beginning of Java 20 years ago, boy, everyone was using inheritance. It was the greatest thing since toast. Nowadays, not that important, not that critical. I don't go around deciding that I have an animal and a mammal and a canine class. It just doesn't show up that much. But it is important for the language. You do see it in a lot of frameworks. We do need it, but it's just not like the most critical thing in the language. It doesn't really resolve a lot of problems, and it's not going to be like something that you use all the time. It's there, it's important, it's in the background. So let's talk about it. Inheritance. You create a new class and behavior based on an existing class, and you get all that behavior and that reuse from your parent class. So the child-parent relationship. Here is a textbook one. Honestly, I have never had an animal class or a mammal class or a canine class, but this is a good example to show you that each one of them is a more specific version of the previous. So what are animals? Well, that's pretty broad. Mammals narrows it down. Canines narrows it down even more. So everything a canine does, a mammal will do, an animal does, right? But not all animals are canines, and not all mammals are canines. But canines are always mammals and are always animals. So if an animal can do something, a canine can do it. If a mammal can give milk, so will a canine. So I can reuse, I can have the same methods, I can have the same properties of my parent. This sounds like great. I have to write less code, or one person writes the class once and then I can just reuse all that. I think that was the theory from a while ago. It really hasn't panned out that much. We don't use it as much as anymore, but it is there. So if you have a child and you have parent classes, you inherit, you get the properties and methods of your parent. It doesn't get used a lot, but it is important. It does get used consistently, but probably not the thing that you'd be doing on your day-to-day basis. Dynamic binding is probably the most important topic, but the hardest to kind of explain until you get into it. So this is the ability to send a message to objects without knowing their specific type. So is this interfaces, is this polymorphism, is this data hiding? No, it's not those things. Those things kind of help out. They're related, but they're not the same thing. It's hard to give you an example or explain how this works without being more versed in the language, but let's give it a try. In this print method, I am taking in a document and a printer. All right, I'm not saying it has to be a PDF document or an invoice, which is a kind of document. I'm not saying it's a color printer or a line printer. I'm just defining, hey, give me a document of some type, literally of some class. Give me a printer of some type of some class, and I'll print it for you. But what makes this dynamic binding? Well, let's pretend I have a list of documents. I have an array. I have a collection of documents. Some are documents, some are PDF documents, some are invoices, and I just have a bunch of documents with me. I don't need to know exactly how to code up, how to print a PDF document, how to print an invoice. If you just give me a document, I'll figure it out. If you just give me a printer, I'll figure it out. So if you define your classes and your methods and your interfaces at a higher level, right? And this is what's kind of important from you as a Java programmer. I don't want to have two methods, one for PDF document, one for invoices, one for color printers, one for line printers. Listen, I can figure this out. You just give me a list of documents and call a print method and just loop through them, and as long as they're documents and as long as they have an associated printer, we can figure it out. So I don't need to know what's in that list. I don't need to know if there's a lot of, the PDF documents or invoices. I don't need to know if they're color printers or line printers. I just need to know that they're of some type, and I don't need to interrogate each one as like, are you a PDF printer? Well, in that case, do this. Are you an invoice? Well, in that case, do that. No, I just know that you're a document, and then that will get determined at runtime what to do with you then. Kind of a hard concept without getting some more specific examples. We'll see those in the language. I'll point it out, but kind of keep this on hold. Maybe put a button in it. We'll get back to it. All right, you just did a whole chapter on this, but does it matter? OOP matter? It certainly does in Java. You need the basic principles, all right? Do you need OOP to learn and to use every day of your life? No. You need the course of syntax and the language itself. Now, a lot of folks went way out of the way to argue that Java is or is not OOP. It's not pure. Those arguments are from 20 years ago. Most programmers know enough of what they need to know about OOP to get the job done, and that's what I need you to learn. Now, we're going to spend a lot more time on interfaces and data hiding, and those things are practical and what you need to learn to become a Java programmer, especially a beginner programmer. When you get to the point that you're designing your own frameworks, designing your own programs, and you're thinking about your code being used by other people, most certainly this becomes a lot more important. But you are probably going to be using frameworks, be using programs that someone else built. You're going to be using frameworks called Spring Boot and .NET. They have the OOP baked into it. You're not going to get there yet, but you need to know how to read it. And at some point, you're going to learn how to change it. And then even after that, you're going to design your own systems. So it does matter. But from your perspective, learn enough of it so that you can get by. And then through some practice and some iteration, you'll get better. You'll be changing interfaces, you'll be changing OOP designs, and then when you become an architect, you can come up with your own OOP designs. But for now, know enough to get the job done. All right, let's talk about what's a class. This is a terrific example of a class. You'll probably use it every day. This is not kind of a theoretical. You will be building websites, and some of you will be building e-commerce sites, and you'll probably have a shopping cart class. You will add things to that class. You will remove things, and maybe, I don't want any of these things, so I'll have a remove all method. So this is not a class or a lecture on UML, but I'm kind of using some of the syntax. The top part is the class name. Notice that there's no spaces. I like the bean format, which is uppercase S and uppercase C for each letter. That's generally how Java is done. The interfaces or the methods or the functions, the contract, there's three of them here. There's add, remove, and remove all. Now, ask yourself, are these all the things you can do in a shopping cart? Absolutely not, but these are good three examples. Here's what I do want you to look at. Why am I adding an item? Why am I removing an item? Why am I not adding, like a bag of groceries? Because if I had to do an add method for everything in Amazon, that would be infinite. But I certainly can add items to my shopping cart. I can remove things, and there are probably enough similar values that I can define an item interface. What's an interface? We'll get to that. But in my class, I have a name, I have methods, and we're going to see in a little bit that those also have properties. But this is an example of a class. We're getting closer to the Java examples. But here's a class. You can do this class in .NET. You can do it in Python, of course. But in Java, here's a good example of a class. Here are some methods, and we're going to get to exactly how to code this up in the next couple of slides. Okay, here's some more on inheritance, specifically a little more real-world examples. We're not talking about dogs anymore. So you might have in your code a customer has a name and a phone number. You may have a specific kind of customer. Maybe it's a corporate customer, and the corporate customers have a TIN. That's a tax information number. A regular customer or over-the-counter customer or a public customer don't always have tax information numbers. And also, if you're just a customer, maybe I don't need to know your social security number. Most likely you don't. But both corporate customers and customers do have names, and they do have phone numbers. So remember that example that all corporate customers are customers? Well, all corporate customers here have names and phone numbers. I don't need to re-implement that logic in my corporate customer because I can just reuse what's in customer. Now, corporate customer does have one extra feature, which is tax information number or get TIN. Customers don't have that. So if I'm just a customer, I'm going to have a name and a phone number. If I'm a corporate customer, I'm going to have name and a phone number, but also a TIN. So this is what I want you to get out of this, is that if I'm a customer, I'm always a customer, and I have those two things. If I inherit from customer and become a corporate customer, I can have more things plus what's in customer. All right, so that's called an is-a relationship. So if you can say that a corporate customer is a customer without sounding funny or without breaking your head, that's kind of inheritance. And that's what the example is here. All right, there's some other examples that things that don't quite fit, but let's start with this one and let's take it from there. All right, so inheritance, we kind of downplayed it a little bit. We had corporate customer and we had customer. That's an is-a relationship. That always was in the textbooks long ago as being like the end-all of relationships. We should be always looking for inheritance. But I will tell you that more likely than not, 95% of the time, you're looking for relationships like has-a. A customer has a shipping address. All right, those exist every day, every minute of your Java programming life. All right, customers have shipping addresses. So that makes sense. A customer is not a shipping address, so that's not inheritance. So please differentiate between the two. Corporate customer is a customer, that's inheritance. A customer having a shipping address means I have something. I have a shipping address. I am not an address. If you get confused with that, just go back to the previous slide and ask yourself, does a customer have a corporate customer? No. A corporate customer is a customer. A shipping address belongs to a customer. It's not is a customer. So take some time with this slide. If you are having problems with this or you're mixing up the words, you're going to struggle. So if you need to watch the slide again, go listen to the previous slide again. Do that. You have to know the difference between a corporate customer is a relationship, inheritance, not used that often, but it's important, and has a relationship, which is used all the time. Really important that you understand that customers have relationships with other classes. Those are has a relationships and critical to the language and OOP in general. Now, you may ask, well, what about corporate customer? I don't see it has a shipping address, but it does. Why? Do you remember in the previous slide? Everything the customer has, corporate customer has. So even relationships. If a customer has a relationship with a shipping address, then I, as a corporate customer, since I am a customer, also have that same relationship. So I own, as a child, I get my parents' methods, my public properties, and relationships. I get all three of those things. All right? That's a lot to take a bite out of. Think about it. Stare at this some more. If you have questions, leave them in the comments. I'll do the best I can to answer, but this is really fundamental. Inheritance is a relationship, used but not that popular, but most certainly customers and has a relationships used every day, every moment of your Java programming life. So understand the difference between the two. All right, if you want to take a break after this slide, do that. Walk around the block, come back, re-listen to this section, go back to the previous two sections, listen to those, and then come back to this. Don't go forward until you kind of have a good understanding of what polymorphism is. All right, you need it for Java. Why do you need it? Because almost everything has this concept baked in. By everything, I mean all the frameworks that you're going to use, Spring frameworks, third-party frameworks. Polymorphism, although it's not always called this, and it's not in the documents, and it has all this in the language. So let's try to put all this together. I have a customer class. All right. Customers have tax rates. Corporate customers calculate their tax rate one way. Government customers calculate their tax another way. And let's just say that their tax rate is always zero, just for laughs. Corporate customers have an incredibly complex system depending on localities, states, the type of product, really super complex. But governments, it's just zero. Corporates, very complex. But both of them are customers. That's the relationship is a. Our corporate customer is a customer. Our government customer is a customer. And they both have tax rates. I can ask them for their tax rate. Now, you could have two separate classes, corporate customer and government customer, and then kind of copy and paste the implementation. But did you have get 10 on one and get 10 on the other one? Do you really want to maintain them in both places? No, I don't. So I'm going to put the tax rate, which I know that both need to implement, that both children, both corporate customer and government customer need to give me a tax rate. All right. I'm going to define that in the customer class. All right. No matter, all children of customers have a tax rate. It may be zero in terms of the government, and corporate customers are very complex, and personal customers, I don't know, but let's just focus on these two. If I have a list, an array, a collection of customers, and I have 10 of them, all right, so let's say I'm reconciling my statements at the end of the day, and I'm on a little program. I have a collection of customers. I have 100 of them. All right. Listen, I don't know what kind of customer you are, but I know you have a tax rate because customer said so, and you're going to give me back a float. So as I loop through my customers at the end of the day, I'm going to call the get tax rate method. And depending who you are, you're going to, at runtime, you're going to give me an answer depending on whether you're a corporate customer or a government customer. I'm pausing for dramatic effect. You need to understand that this is where polymorphism comes in quite handy, very important. I don't have to have different classes, different interfaces. I don't need to get government tax rate. I don't need to get government corporate tax rate. I can just say get tax rate, and depending on what kind of customer you are, you're going to churn out and give me an answer, but it's going to be the same contract. We're going to see this in the language. Pause here, think about it. Pausing. Your next question might be, well, wait a minute, why isn't get 10 in customer? Why do I see them repeated in the corporate customer and government customer? Well, customers don't have always have tax information numbers. Remember that? We said that last time. So I'm not going to put something that, even though both government and corporate customers have TINs, I'm not going to put it in the customer class because not all customers have TINs. So these are the choices I need to make. Everybody has a tax rate, no matter because that's fundamental to being a customer. But not everyone has a TIN. That only belongs to corporate and government customers. You may have a better way to resolve this. You may say, well, couldn't I have another interface for corporate customers and government customers? Sure, we can get that discussion. But what I want to point out is that customers have tax rates by definition in our little design, in this little world. And if I have a collection of customers and I call get tax rate, I'm going to get a tax rate because I know a corporate customer is a customer, a government customer is a customer. You promise to give me a tax rate no matter who you are, and this is the important part of polymorphism, is that I don't need to loop, when I loop through my customers, I don't need to ask what kind of customer you are. Just to the fact that you're a customer, at runtime, you're going to implement your instance of your class is going to determine how to get the tax rate for me. All right, you still with me? Hang on. Last concept, last slide. There's a lot to take in here, but this is really important. Inheritance isn't what you think it may be. It's not the most popular feature of OOP. Interfaces are. Now, you may ask, wait a minute. Now I have a taxable interface. Get tax rate used to be on customer. Why did you take it out? Why did you put it in a separate kind of construct? Why is it now an interface? Why isn't it just part of customer? That's because I realized that get tax rate is taxable and it can be applied in different areas. It doesn't just have to be in corporate customers or government customers. So what I did is I went ahead and took it out of here and made it its own thing, so that taxable is its own interface. Now, a customer still implements, it still realizes an interface. It's still taxable. A customer is taxable. So, you see how that tax rate is get tax rate, which returns a float? Corporate customer and government customer are children of customer. They don't know that the method is out of customer is now part of taxable. Hey, I'm still going to implement a get tax rate, whether it's in customer or a taxable interface. I still have a tax rate job to do, and I'm going to do that for you as long as you define it. So those classes don't change, but I peeled out the tax rate from customer to taxable. Why did I do that? All right, let me show you on the next slide why I did that. Wow. Okay. This is why I did that. Something that is taxable isn't just a customer. A bond could have a tax rate. I'm like, wait a minute. That's crazy. Customer and bond have nothing to do with each other. You're right. They don't. But my method of getting a tax rate is applicable in other areas, even those that have nothing to do with each other. They're just things that are taxable. They are not an is a relationship. So taxable is not a corporate customer. A bond isn't a corporate customer. It's like, oh, wait a minute, you're confusing me. What's going on here? This is an important topic. That interfaces are just responsibility functions that you as a class need to implement for me. I defined the interface. Listen, here's a tax rate and it's a float. Can I use it as a customer? Yeah, a customer has a tax rate. A government customer is a zero, actually. A corporate customer has some complex algorithm. And a bond has a tax rate too. So things can be taxable that are not in a hierarchy. They're just an interface that need to be implemented. Why is this so important? Why do I care about this? It's because I'm more interested in interfaces than I am in hierarchies. I'm not going to define a dog and a canine and all that, but most certainly I will define interfaces. And that is going to be a contract that I can use in different parts of my program. And as long as you implement the interface, then I know I can always count on you to do this. And this is a powerful, or the most powerful part of OOP, is that by defining interfaces and applying them to classes, and then for those classes that implement those interfaces, I can treat them the same. So I don't need to have a get bond rate. I don't need to get customer corporate tax rate. I can just have a get tax rate, and we're all good with that. And it's always going to return a float. Was this a lot? It is a lot. Please go back over the slides. Keep all this in your head, and when we do the language exercises and we do the labs, this will come up, and you'll see why this is important. And this is the difference between Java and other languages that are not OOP. You need to know these things. This Java is not just a syntax language. It's not C. It's not functional. There is a lot to take in before you can start using the syntax. The syntax assumes that you know these concepts. All right. So let's summarize in the next slide. But if you're confused, go back to the previous slides. Maybe go watch a couple other slides from someone else. Get these topics. You got to understand them. Otherwise, the whole language doesn't make sense. So let's go to the next slide. Let's summarize, and then we get to the syntax. Okay, here's the big summary. So inheritance and interfaces. Let's compare the two. Inheritance is used when you have an is-a relationship. A corporate customer is a customer. A canine is a mammal, is an animal. Okay, it's a subclass, it's a parent-child relationship. You use it when you want to reuse code from the base class, when you want to establish a clear hierarchical relationship in your code and in your design and in your business world that makes sense. And you want to extend or modify the behavior of a base class. This was sold many years ago as a way to get reuse and save a lot of time, and that you would put all the code in the parent class, and the children would implement it, and you would do so little coding, and everything has been done for you. This hasn't really happened, but inheritance is still critical and important to learn. But the kind of reuse and the functionality and the kind of value from inheritance, probably I'm going to poo-poo it a little bit. Not as important, still, but not as used as much, but still important. On the other hand, what is really used a lot? What is critical? What can't you ignore and still learn this language? And that's interfaces. So interfaces define a contract, a function, for behavior that you do not provide the implementation. Remember that taxable? Listen, you're just taxable. I don't know how you do it. Maybe you go to a list, and maybe you go to the state, and maybe you go to a database, or maybe you just say 0. These are used to define a standard set of methods that you must implement. So you use interfaces in all these places, and this is a lot, and this is fundamental to the language. When you want to enforce a set of methods that must be implemented by any class that adheres to the interface. So if you're loggable, that you can log, that you're printable, that you can print, that you're taxable, if you adhere to that, if you promise to adhere to that method, then please implement it for me. And then when I know that you're just a printer, you're just a logger, that you're just taxable, I can ask you, give me that answer. I don't need to know what kind of logger you are. I don't need to know if you're a line printer or a color printer. I don't need to know if you're a government entity, if you're a bond. If you have a method and you defined it as an interface, then please implement it and give me the answer. Okay, that is a lot more common. We're going to see that interfaces all over in the language. Inheritance some, but interfaces you got to learn. All right. So you want to ensure that unrelated classes share a certain behavior. So why do I want to do this? This seems like a lot of work. Why can't I just copy and just cap two different functions that neither one of them need to worry about each other? That's because you as a Java programmer are going to be programming for an interface, not in really an inheritance. Your designs and that you build, that you use, and other people have built for you are based with this concept that I have common behavior, I have common methods that I just know need to be done, and that anyone who adheres to this, I can treat the same way. This is an important concept in the language. It comes up everywhere. When you start using frameworks, you start using other people's code, interfaces are part of that. Of course, they can be abused and be too much, but they are core to the language. So I implore you, take a look at the previous slides, come back to this, and in the next section, in the next other topics of this course, we're going to see where this comes up. All right? Okay, so we had to go over this material. All right, you need these concepts, so let's summarize them. And in the next chapter, we're going to start going over syntax and how to do Java. But what you learned in this chapter was we discussed object-oriented programming. We had examples of classes and objects. We talked about polymorphism, dynamic binding, is-it relationships and inheritance. We talked about has-it relationships, the all-important interfaces, and the difference between the two. All right. I will iterate one more time the difference between interfaces and inheritance. One is an ISA, one that we use to define a hierarchy. Okay, a mammal is an animal, a canine is a mammal, a government customer is a customer. When we have that kind of hierarchy in our design, we're going to use inheritance. But more likely than not, we're going to be defining interfaces where we enforce specific methods across different classes. So we're going to define a taxable, we're going to define a loggable, we're going to define a printable, and then, hey, if you adhere to that, then that's great. Then you are my type, and that you promise to implement that, and then people calling you can rely on you for doing that. All right. So that's the difference between the two. And finally, we're always going to prefer composition over inheritance. Sorry, gods from 20 years ago. I always like to have has over is-a. It's just easier for me, and I'll show you why in the next couple sections. But this has been the summary for this section. And now let's go talk about some syntax.